Theorem 2.6, from a point external to a circle, the two tangent segments are congruent. This is a circle O here, and there are two tangent segments, and from this point A outside of the circle. So it's basically we have a circle first, and there's a point outside the circle, and we can draw two tangents to the circle, and we want to prove that these two tangents AP and AQ, they are congruent. And this is very similar to one of the problems we have learned before, that it's kind of like the angle bisection bisector, the theorem we just mentioned, theorem 1.12. The point is on the angle bisector if and only if it's equidistant from the sides of the angle. So it's very easy. There are many different ways here. The proof I give here, I try to prove these two triangles APO and AQO are congruent. First of all, because they are both right triangles, that's by the definition of tangent. If this is since AP is a tangent, OP is perpendicular to AP. And similarly, OQ is a tangent to AQ. So these are both right triangles. And now we want to prove two right triangles are congruent. For a special triangle, right triangle, we have two properties. HL means hypotenuse and one of the legs. And then there's another one is HA, hypotenuse and acute angle. So here we can clearly see they share a hypotenuse AO, and the two legs PO and OQ, they are congruent. So it's very easy if we use HL. These two triangles are congruent, and because PO is the radius of the circle and OQ is also the radius of the circle, so PO is congruent to QO, and they share the same side AO hypotenuse. And by the congruent parts of congruent triangles property, AP must be congruent to AQ because they are corresponding sides of these two triangles. So it has been proved here. So we can, in the rest of the sections, we can use this theorem. Next one, 2.7. A circle can be inscribed in a quadrilateral if and only if the angle bisectors of the four angles of the quadrilateral are concurrent. We talked about a quadrilateral can be inscribed in a circle in section 2.1 if and only if the two they have a pair of opposite angles add up to 180. So if we have a pair of opposite angles, the degree sign is 180, then this quadrilateral can be inscribed in a circle. But here we want to talk about the circle is inscribed in quadrilateral. So what kind of quadrilaterals can have an inscribed circle? By this theory, it says the four angles are the angle bisectors of four angles are concurrent. We have proved if we have a triangle, any triangle, the angle bisectors must be concurrent. But is that true for quadrilateral? Not necessary. We can try quadrilateral, for example, a rectangle, and then we can draw angle bisectors, and they may not be concurrent. So here, but if we want to inscribe a circle inside the quadrilateral, we must have to have this condition: the angle bisectors of four angles are concurrent. This is if and only if condition. So we have to prove both necessary and sufficient conditions. The sufficient condition, number one, if the angle bisectors of the four angles of the quadrilateral ABCD are concurrent, then a circle can be inscribed in ABCD. First, we prove the sufficient condition. Here we're going to use theorem 1.12. let O be the intersection of the angle bisectors. So we already have 4 angle bisectors, and we know they are concurrent. So this is given. So we can take the 4 angle bisectors, and the intersection is O. And by theorem 1.12, a point is on the angle bisector if and only if it is equidistant from the sides. So because we know this point O is on the angle bisector, so it must be equidistant to both sides of AB and AD, and also AD and CD, and also CD and BC, and also AB. So we know the distance from O to 4 sides of the quadrilateral is the same. So that's why how we have QO is, look at the second picture, QO is equal to PO and SO and RO. So we can draw a circle with the radius equal to PO, QO, SO, RO, and such that the circle is tangent to all these 4 sides. So that's the sufficient condition. Now let's look at the necessary condition. Necessary condition is the converse statement of the sufficient condition. So if a circle can be inscribed in a circle, so we know we have a quadrilateral and we can draw a circle inside tangent to 4 sides, then the angle bisectors must be concurrent. So first of all, we let O be the center of the circle. So we can, if O is the center and we already have a circle inscribed inside, we can draw these radius tangent to the perpendicular to all the 4 sides. And by theorem 1.12, if a point is equidistant from 2 sides of the angle, then this point must be on the angle bisector. So clearly here O should be, because PO is congruent to QO because they're both the radii, by theorem 1.12, O must be on the angle bisector of A, the angle A. So if we connect AO, that's going to be angle bisector. Similarly, we can prove the others because QO is congruent to RO, O is in the angle bisector, on the angle bisector of D, and again O is on the angle bisector of C, O is on the angle bisector of angle B. So that means all the 4 angle bisectors are concurrent. So the theorem 2.5, the last homework assignment, is similar to this proof. Now we look at the example 2.2. Prove that a circle can be inscribed in every kite. A kite, the definition of a kite has 2 pairs of adjacent sides. So if we look at this kite here, BC and CD are congruent, and AD and AB are congruent. We want to prove that we can draw a circle inside. Well, actually the picture is not exactly correct. I'm going to use the last picture. Suppose this is a kite. AB is congruent to AD, BC is congruent to CD, and we have an inscribed circle. We want to know if we can draw an inscribed circle. By the last theorem we just proved, theorem 2.7, when can a circle be inscribed in a quadrilateral? If the angles, the angle bisectors of the 4 angles are concurrent. So clearly we have proved something in previous sections. We know if we draw, if this is a kite and the diagonals AC and BD, the BD will bisect perpendicular of AC AC. If we look at this picture, this kite here, 2 diagonals of kite AC and BD, they we have BD well, actually, AC is a perpendicular bisector of BD because A and C, vertex A and C, are the points where the congruent sides meet. Because AB and AD are congruent, they meet at A. BC and CD are congruent, they meet at C. So AC is not only perpendicular to BD but also bisects BD. And also we proved that AC is an angle bisector, which means so the diagonal AC is an angle bisector of angle A and angle C, but BD may not be an angle bisector, so we cannot use the diagonal BD, but we can easily try to find a point on AC that such that, for example, a point K here such that BK and DK is the angle bisector. And so we construct an angle bisector of one of the angles, for example B, and intersecting AC at K. So suppose we draw BK, which is an angle bisector of angle B, and then we connect D and K. But D and K, we may not know if it's from the construction. We don't know if DK is the angle bisector, but we can prove DK must be angle bisector. This can be proved by congruent triangles because, or we can use the congruent triangles BKA and DKA. This can be verified by S. And so these two triangles are congruent. That means the angle ABK and ADK are congruent. And similarly, we can prove the triangles BKC and DKC are congruent. That means the angles CBK and CDK are congruent. So that makes CDK and ADK are congruent because CBK is congruent to ABK. So that's the proof of DK, why DK is also a bisector. So that means K is the intersection of 4 angle bisectors. We already know AC, the diagonal AC is the angle bisector, but diagonal BD is not guaranteed to be an angle bisector. But we can always find the angle bisector of one of the angles, and it must connect to the intersection point with the other vertex. It must also be an angle bisector. So that's how we proved 4 that angle bisectors intersect concurrent at K. And by theorem 2.7, if 4 angle bisectors are concurrent, then we must be able to draw a circle inside. So this is the proof.